Good morning, welcome. In this morning, first I'm going to talk about the statistical or stochastic version of the model, and then I'm going to talk about 3D VAR. That will be the first of the method that most of the people in data assimilation are used to. So I'm building towards that. So what is the model we are going to start? Same starting point. Z is equal to h of x plus v. Observations have noise in them. V is the observation noise. Generally, I assume V to be Gaussian distributed with a zero mean and variance R. Here, I want you to remember Z, V, they belong to Rm, X belongs to Rn, H belongs to R, M by N. And this matrix R is a M by M matrix. It's a M by M matrix. This is called the covariance matrix. I'm assuming everyone is aware of the normal distribution. How many have heard me? Normal distribution in one variable, normal distribution in multivariable. So this is called multivariate normal distribution. Multivariate normal distribution. So for the sake of completeness, let me write down the formula for the distribution for the normal. I will write here for later reference. X is a random variable. Suppose normal m sigma square means the probability density function of x, p of x, is equal to 1 over square root of 2 pi sigma exponential of minus x minus m whole square divided by 2 sigma square. Here, x is a real random variable. When x is a vector in Rm and x belongs to normal m sigma, I'm using R, right? I'll use the same thing. R, what does it mean? The probability density of x is equal to 1 over 2 pi to the power m by 2, determinant of the absolute value of the determinant of R, exponential minus x minus m transpose R inverse minus 1/2 of x minus m R inverse x minus m. So this is called the determinant of R. It's very important for you to be able to know the functional form of the normal distribution for a single variable, and this function is generally denoted by the bell-shaped curve. This is the m. The spread is a measure of sigma square. Are you all in my place? So this is the univariate normal. This is the multivariate normal. Here m, I don't want to confuse this m with this m. So let me call this vector A, vector A, vector A. So A is a m vector. R is a m by m matrix. R is called the covariance matrix. A is called the mean vector. The normal distribution in m dimension takes this form. This is the functional form of the normal distribution in a m dimensional space. How many of you have seen this? How many of you know this? Seeing is not knowing. I'm now going to tell you a very famous Chinese proverb, which I hold on to very dearly. I'm going to say it and then write it for you. You hear, you forget. You read, you remember. You do, you understand. All of it, me? Come on, guys. I want each of you to print this and put it in your study at home. Hearing is not knowing. Knowing is not knowing to do it. If you do it, you know it, you can talk about it. So I want to write that you hear, you forget. You read, you remember. You do, you understand. You understand. You cannot say, I know cooking until you can cook. Cooking is doing, right? You cannot say, I play tennis, I know tennis until you play tennis. Mathematics is no different. So please understand. So that's why I ask a question, do you know it? Do you know how to do it? Did you hear it? So you should be able to write down these formulas. So what does it mean? This is the mean, this is the covariance. I'm assuming everybody knows what a mean, covariance, variance and everything else, so on. So I'm not going to go into that. So that is what we mean by when we say the V is a vector 0. Okay, you may wonder why this assumption. Right from the early days, who invented this normal distribution is also called Gaussian distribution. Normal distribution or Gaussian distribution. So Gauss, in the early days working with astronomical data, he found that there are errors in the observation. He wanted to find out the behavior of the observational errors. He plotted histograms and he fitted the histogram with this function. Ever since, it has become a model for modeling errors in observation. And in his honor, this distribution is called Gaussian distribution or normal distribution. So it was invented by Gauss over 2 centuries ago. So it is not unusual for us to be able to assume that the errors are normally distributed. Normally distributed errors can take positive, negative values, but they are concentrated around the mean. So that's the basic idea of that. Good. And covariance matrix. So this noise, we know it affects, but it's not observable. I cannot separate the signal from the noise. So this is the signal part, this is the noise part. The last class, to make life simple, I assumed that there is no noise because we have to make progress slowly and steadily. All of it, me? So in the presence of noise, how does the method of estimating X knowing Z differ from what we did in the last class?
Sir, why are you taking mean as 0? Is it just because of...
Why are we taking the mean to be 0? Okay, I'm assuming my instrument is well calibrated. Yeah, that's right. If the mean of the noise is not 0 means what? There's always a bias. You all have a weighing scale at home? That's right. In the morning, everybody wants to weigh themselves. If the weighing scale, when there is nothing, shows +3 means what? Your scale is screwed up. So you weigh and then subtract 3 from that. So that's the idea. So when I'm assuming I'm trying to measure something, I'm using instruments, I am calibrating the instrument so that the bias in the instrument, well calibrated, is the bias is 0. But then there's a natural variation. For example, the temperature. Temperature in Bangalore 8 o'clock. Are they going to be the same every day? No, it depends on the season. It depends on, so within the same month, is it going to be the same? No, there are natural variations. the wind, and everything else. And then there's a measurement error. So there are quantities like temperature, pressure. There is a natural variation from day to day. And the top of it, when I'm trying to measure it using an instrument, the instrument also introduces an error. For example, let us say I buy a voltmeter cheap for 500 rupees. The manufacturer will tell, this voltmeter will read from 0 to 200 with a 10% error. But if you give 5,000 rupees for a voltmeter, then they will say, this voltmeter can read from 0 to 500 with 1% error. Are you with me, please? Cheap designs. So that's called the measurement error, and that's what is modeled by Gaussian. So what are we now going to do? We are going to talk about Z minus, okay. And what is covariance matrix? Let me talk about that. Without loss of generality, I'm going to assume the covariance matrix R is diagonal. When M is 2, how does the covariance matrix looks like? Z, sigma 1, sigma 1, sigma 2, sigma 1, sigma 2, sigma 2 square. This is the structure of the covariance matrix for the case of M is equal to 2. So this is the cross, there is a row here, there's a row here. Row is the cross covariance between the two. Everybody? When rho is 0, means what? The first measurement, the second measurements are not correlated. So in this case, R becomes sigma 1 square 0, sigma 2 square. Then if I use the same instrument to measure different components, then these are same, which is equal to R is equal to sigma square times 0, 1, which is equal to sigma square I. So there are various gradations. So when the off-diagonal elements of R are non-zero means what? The measurements are correlated with each other. Let me give an example. I have a thermometer to measure the temperature here. I have a thermometer to measure the temperature 100 feet from here, 1,000 feet from here. So there will be correlation between the two thermometer readings which are separated by a shorter distance. There will be less correlation between two thermometers at a larger distance. Are you with me, please? That's right. So that's what correlation is all about. But what I do here, does it affect you? Or what happens here, does it affect you? That's correlation. What I do here does not affect you, there is not correlation. So without loss of generality, I'm going to assume that my matrix R is this. But, so there are three levels of assumptions in here. General, diagonal, and diagonal are the same elements. These are the three different classes of assumptions one can make depending on how you do what you do. Today's temperature was correlated with yesterday. Today's temperature was almost no correlation with the week past from today. A month, there's no relation. A year, there's no relation. So if two events are temporally closer apart, they are correlated. If two events are temporally separated, there's less correlation. If two events are spatially separated by a shorter distance, they are correlated. If two events are separated longer distance spatially, whatever happens in Delhi doesn't affect Bangalore. So spatial correlation, temporal correlation, correlation length. Correlation length refer to those that are correlated within that time frame. So these are all the concepts that one need to understand when you deal with observation, correlation, measurement errors, and modeling observational errors. Are you all with me? So that's a science in itself, and that's very much related to the probabilistic density. Are you with me? That's right. That's right. So what is that we are going to do? This diagonal element, if it is this type means what? The first one has covariance sigma square, second one has a covariance sigma 2 square. They are all different. If the errors are such that variances are different, it is like mixing apples and oranges. I need to scale them to the same unit. Are you with me? Without scaling, the comparison will not be fair. The big guy always will try to dominate the show. I want to be able to introduce democracy. That means every data must have the same say in your decision process. So that calls for scaling. So if I don't assume this part, even if it is diagonal, this requires scaling. All of you? How many of you with me? The need for scaling. So in data analysis, this is called pre-processing. Yesterday we talked about anomalous variables. You remember? Outliers. Outliers are going to be identified by pre-processing. Scaling is also a pre-processing. So before you put things into the data assimilation system, check for outliers, check for scaling. So that when you get the result out of the analysis, you are able to give credit to different observations in an equally possible way. Are you with me? So what is one way of scaling? If x is a normal random variable with 0 sigma square, how do I scale it? I'm scaling it to z, which this z is not the same as z. This is the standard z we use, by sigma. And this z is also normally distributed with 0 mean and unit variance. How many of you remember this? How many of you know this? I'm subtracting the mean from the random variable and normalizing it by the standard deviation. The z is the normalized version of x. And what is the beauty of z? The z is 0 mean and unit variance. All of you? How many of you with me? That's right. That's what called z-score in statistics. You may remember that. Z-scores. So this is the way you do the z-scores for a single random variable. How am I going to do the z-score for my problem? For the problem that we have. The way we are going to do it is as follows. You remember my j function, j of x? I don't want to repeat everything. What is j of x? J of x is the sum of squared errors. Here it has to be weighted sum of squared errors. Why do I need to weight? Because of scaling. So j of x was sum of squared errors. Here it is going to be weighted sum of squared errors. So yesterday I had z minus h of x transpose z minus h of x. Today I'm going to have z minus h of x transpose or inverse z minus h of x. So many of you, when you read papers, you may have seen expressions of this kind. What is this r? This r is this r. It is the inverse of that r. So this is called the weighted sum of squared errors. Weighted sum of squared errors. This is simply sum of squared errors. Now, I want to show that this weighting is related to this. So let's find out z square. What is z square? Is x minus m by sigma square, which I can write as x minus m sigma square inverse x minus m. X minus m is a scalar, so without loss of generality, I can put as transpose. What is sigma squared to the power minus 1? I'm dividing it by the variance. Everybody please. How many of you with me? Does this look like this? So instead of x minus m, I have z minus h of x. Instead of x minus m, I have z minus h of x. Transpose. Instead of sigma squared, I have r. Because R is a covariance matrix. R is a covariance matrix. All of you? That's right. Before I go further, I also want you to recognize a couple of things in here. So z is a random variable. So what is the expected value of z? Is equal to expected value of h of x plus v. The expected value of the sum is the sum of the expectations, which is equal to e of h of x plus e of v. E of v is 0. That's called E. But h of x is deterministic. That's h of x. So the expected value of z is h of x. Are you there? That's right. So z becomes a random variable whose expected value is what I want. Okay. Now, what is the covariance of z? And what is the property of the covariance? This is equal to z minus, the covariance z by definition is the expected value of z, I'll write it here, the expected value of z minus e of z transpose z minus e of z. That's a formula for expected value. You all remember that? That's expected value of the covariance. How many of you remember the formula for the covariance? Hey, these are all coming from statistics. Statistics is a prerequisite for this course. Are you all in my place? For those of you, I don't see too many nodding heads. What is the definition of a variance? So let x be a random variable. This is called the mean. What is the variance? What is the formula for the variance of x? Which is equal to e of x minus e of x whole square. You subtract the mean. Everybody please square it, find the expected value. Subtracting the mean from the random variable in statistics is called centering. You center the variable with respect to the mean. So this is the centered random variable. Centered random variable. And if you have a vector m, I have expected value of that. The covariance of x must be equal to e x minus e of x. That's a column vector. I need to get a matrix which is equal to x minus e of x transpose that. So this is a column vector. That's a row vector. The outer product matrix, expected value of the outer product matrix is the covariance matrix. You remember the outer product matrix we talked about the very first class? That's right. So these are the basic definitions. Variance of a scalar, variance of a vector random variable. I'm trying to apply that same thing in here. The E of z is h of x. Z is equal to h of x plus v minus that. So what is this? This is equal to v transpose. What is this? This is equal to v. So this becomes the expected value of v transpose v, that's equal to r. All of you, please, good for you, please. How many of you are with me? That's right. What is the definition of democracy? One vote, one person, every vote carries the same weight. Are you with me? That's democracy. So if I have a vector with several components, I don't want any one particular component to dominate my show. That we saw in the last class. If there is an outlier, the outlier is a big guy. We found out the least square estimation, the outlier, the big guy, has a larger say. So the data quality people have to shave off the outlier by making sure that it's a true outlier or is the real signal. That's what's called the pre-processing of data. Suppose you have a meeting of the people at the same level. Everybody has one vote. But the meeting is presided by the director of the institute. If the director says something, no one wants to talk against it, right? But if the director goes out, everybody will shout. Haven't you seen that? That's right. So in that case, not everybody has the same vote. The director's opinion carries larger weight. We shall do that. That's what the director will say. Everybody will say, yes, sir. You put your sleeves up and go to work. So there are two types of meeting. In one meeting, everybody has the same vote. In certain meetings, a person who is in power has a bigger vote. Or in a meeting, if there may be certain experts who may have known the topic of discussion much more better than the others, their voice carries more weight. Are you all in the place? That's right. So, meeting, everybody equal, equal representation, unequal representation because not everybody knows the details of the topic being discussed the same way. So those who know will have a greater voice. All of you? So here, I don't want any one particular observation to have a greater voice. So I'm standardizing it. This standardization in the univariate case looks like this. When you extend it to multivariate cases, look like this. So that is the starting point for statistical least squares. Are you with me? Do you see the difference between deterministic least squares estimation and statistical least square estimation, where the observation is corrupted by noise? So what is that I'm assuming? I don't know what is the actual value of the noise affecting me, but I do know the gross properties of its covariance. So I am assuming the knowledge of R is known. So what are the things that are known? H, Z, R are known. And how do you know R? If I'm measuring with the voltmeter, I know the voltmeter will tell you what is the result. Let's talk about satellite measurements. If it is a new satellite, if you can look at the design manual of the satellite, they will tell you what is the accuracy of the measurements from the satellite. But the satellite has been in service for 10 years. Anything that lives longer changes its properties. Are you in my place? A voltmeter, 10-year voltmeter is not as accurate as it was when we bought it first. So what is the problem in using satellite data? You know satellite data has errors, but no one knows the properties of the covariance of the satellite errors. So what do? You pray the good Lord, whomever is your Lord is, assume there is no error, get on with life. That's a fact. Radar meteorology, radar data. If the radar is looking at a hurricane, the radar is looking at a plane, a radar is looking at a cloud system. The variances are different. I may know the radar variations when it was made first, but as the radar gets aged, no one knows, no one calibrates it. At least radar you can calibrate it. Satellite, who calibrates it? Whatever the satellite gives you, you take it as the word of God, don't you? So I want you to understand now, this theory has a direct implications on what you do. If your data comes from satellite, you just don't know the error properties. If the data comes from radar, oftentimes you don't know the error properties. If the data comes from the instruments, then you have to look at the manual of the instruments. Everybody plays. So knowing R is a big challenge. But we do know there is an R. Are you all in my place? In practice, there is an R. But knowing R is a difficult problem. So that's one of the challenges in data assimilation, using especially satellite data, radar data, instrument measurements, or whatever measurements you are going to get it from. So with that, I have formulated the problem. I'm now going to have to. So what is the basic thing? Minimize with respect to x belonging to R and j of x. So I formulate the problem, use the principles of statistics. I make sure everybody has the same say by scaling. I come into a criterion which is called scaled or weighted least squares. Are you with me? I want to show you m. So let's assume the case of m is equal to 2, just for the fun of it. So E of x is equal to E1 of x and E2 of x. Let R be equal to sigma 1 square 0, sigma 2 square 0. I want you to be able to understand E transpose R inverse, E transpose, say this is, I'm sorry, E transpose R inverse E, that's exactly this, right? This is equal to E transpose R inverse E. So I'm going to give you an example of this in here. So what is this? This is E1x, E2x, sigma 1 square 0, sigma 2 square, E1x, E2 of x. And what is this? This is going to be sigma 1 square E1 square x plus sigma 2 square E2 square x. Are you with me? So your sigma square is larger than this. He has more say. The sigma 2 has larger than this. He has more say. So by dividing by the inverse of this, what is it I'm trying to do? I'm trying to convert this into a z. I'm going to convert this x to z. Hey, that's... So this is z1 square, this is z2 square, normalized, they have the same scale. How many of you are me? Come on guys, please, we need to understand why we do what we do. Why we do what we do. Good, I hope you are with me. Okay, so the problem formulation is done. I spent about half an hour to formulate the problem and convert it into an optimization problem. You multiply, you get 4 terms. Are you with me? You have to compute the gradient, you have to compute the Hessian, you can equate the gradient to 0, you have to make sure the Hessian is symmetric positive definite, you get the solution. Am I talking like a broken record now? Say yes. That's right. The path is the same. Once you get the criteria, it is optimization, it's mathematics, there's no data assimilation. So that's why I tell you, when you do data assimilation, you have to tell, is my difficulty in optimization? Is my difficulty in statistics? Is my difficulty in probability theory? Is my difficulty in matrix theory? Are you there? Because it's a mix of so many different ideas. So I'm quickly going to do that. In order to be able to minimize it, I need to come. So this is equal to Z transpose R inverse Z. This guy has to be interposed. So this must be minus 2 times Z transpose R inverse HX plus X transpose H transpose R inverse HFX. You remember why you get the two there, right? You will get 2 terms, they'll be equal, and they'll get the 2. Same idea. I don't want to repeat, I don't want to waste your time. Everybody? You will get 4 terms. 1 term is a constant term, 2 linear terms. The 2 linear terms are equal. We have already talked about it at great length. I don't want to repeat and bore you. And this is a quadratic term. So this is a quadratic term. This is a linear term. This is a constant term. So what is the only difference? R inverse is stuck there. R inverse is stuck there. R inverse is stuck there. R inverse doesn't affect directly your gradient. Are you with me? So how many of you now understand going from here to here? That's right. Now I'm going to do the gradient of J. 0 minus 2 times. You remember, I have to rewrite this as A transpose X. This will be A transpose. The derivative of A transpose X is A. So this will be equal to H transpose R inverse Z. That's the derivative of that. And what is the derivative of that? Plus 2 times H transpose R inverse H effect, that's a quadratic term. I'm not trying to do anything different. I'm simply carrying through. I'm using the same logic. What are the two logic I'm using? I'm using the same two formula. If F is equal to A transpose X, gradient of F with respect to X is equal to A. If F is equal to X transpose AX, gradient of F is equal to 2AX. These are the two formulas I use. Are you all with me? That's exactly what we did around the same time 24 hours ago. You all have an aha? That's right. So what is the Hessian for that? Is equal to 2 times H transpose R inverse H. H is m by n. So this matrix is a n by n matrix. Now I have to equate this to 0. 2 gets cancelled. So what do I get? The gradient equation now becomes H transpose R inverse H of x is equal to H transpose R inverse Z. That's called the normal equation. If R inverse is identity, if R is identity, R inverse is identity, I get back the whole system. Are you with me now? So from what is the difference between the statistically squares and the deterministically squares is the presence of R inverse. So if H is a full rank, okay, now look at this now. R inverse exists only when R is non-singular. Arithmetic covariance matrix is, I'm assuming to be non-singular, R inverse. So if the rank of H is full, again, this matrix will be full rank. So if rank of H is full, what is meant by full? Is equal to the minimum of M and N. This matrix is H transpose R inverse. H is non-singular. Therefore, my least square solution X star is equal to H transpose R inverse, H inverse, H transpose R inverse Z, which is equal to H plus Z, where H plus is equal to H transpose R inverse, H inverse, H transpose R inverse. That is the generalized inverse. All of you? All of it, me? That's right. Now I'm going to specialize it when R is identity. Just to be able to get the whole result from here, I'm just going to make that argument. Can I erase this part? Come on, guys, please. To be good in data assimilation, you need to remember a lot. I'll give an example. A doctor, a surgeon. After opening the heart, let's assume he's going to do a bypass. After opening the heart, can he say, oh, I have a doubt, I want to look at the book? Come on, guys, I want to think about that. He would not have gotten the degree then, right? That's right. So a doctor, a surgeon Generally, the surgery is scheduled for the very early morning tomorrow. So the previous afternoon, what is that he will do? He will go and meet with the patient. He will look at all the records. What is it I'm going to have to do the surgery on? He will look at all the physical conditions, and then he will decide, can I alone do it with an anesthesiologist, or I need additional help because there's a likelihood for complications. So he has to arrange the team. And he can't tell after he opened the heart, hey, call this guy, get this medicine. No. Preparation. Memory. There's no book in the operation theater. Are you with me? That's right. So a good doctor is one who remembers many things, everything that he has to do. The more you remember, the better you are going to be, no matter in surgery, but also in data science. Everything you have to look back. Then what is it you remember? Are you with me, please? That's right. And how do you tend to remember things? Only by doing. You may not have ridden a cycle for 10 years. But after the 10th year, if I give you a cycle, you will ride it. You may have not swimming for 10 years. But if I throw in the water, I know you know how to swim, right? There are certain things. Why? You have already experienced cycling. You have experienced swimming. Mathematics is the same way. You have to experience by doing. Once you do it, it never leaves you. Even if you want, it doesn't leave you. All of you with me? I cannot emphasize more the importance of doing. Importance of doing. Good. Now, let's assume R is equal to sigma square I. In this case, R inverse is equal to I by sigma square. With me? So let us substitute this in here. So X star is equal to H transpose I by sigma square H inverse H transpose, this is 1 by sigma square I Z. Are you with me? Now let's, so this I by sigma square, what is that I can do? This is, that's the inverse. So this is equal to 1 over sigma square H transpose H inverse. H times sigma square, H transpose times sigma square Z. But this inverse, when I'm applying to this, is sigma square H transpose H, 1 over sigma square H transpose Z. These two gets cancelled. These two gets cancelled. So I get the old formula back, H transpose H inverse H transpose Z. That's my old body. All of it, me? That's right. So what is the result? What is the conclusion? If I have a measuring instrument where all the instruments have the same variance, the weighted problem reduces to the unweighted problem. The weighted problem is different from the unweighted problem only when the different instruments have different characteristics. So the R inverse inside, the R inverse, they cannot cancel if this is not a matrix of this form. So that's a special case. If all the variances are same, then there's no need to wait, because we are equally good or equally bad. All are same. The reason for waiting comes in because the difference in our expertise. You always give more weight to a person who has more expertise than the other person. You always listen to an expert. Are you with me? That's the idea. That's the idea. All of you? Come on, guys. Yeah. Did you understand this part? Yes. Did you understand this part? Okay. So this is a constant, right? I'm going to, the constant lies within the inverse. The constant can be taken out. So the inverse of the inverse is that. Okay, this is the denominator. So these two get cancelled. Let me write that down once more. 1 over sigma square H transpose H inverse H transpose by sigma square Z. Are you with me? Okay. So A times A inverse is equal to A inverse, where A is a constant. Are you with me? Is it yes or yeah? Yes. Yes. Oh, good. That's it. That's right. And that's exactly what I'm using. So what is this? This is the inverse of that. H transpose, H inverse, H transpose by sigma square Z. But what is that? That's sigma square. Sigma square gets cancelled. That's right. That's it. So I get back H transpose, H inverse, H transpose Z. This is the X star I got yesterday for the unweighted case. He still keeps looking at the sigma square 1 over sigma square inverse. What's up? What? Inverse of inverse is itself, right? So here is the numerator, here is the denominator, they get cancelled. Or to put it another way, I will tell you one more way, sigma square times H transpose Z. These two cancel each other because they are inverse of each other, right? That's it. All of you? That's right. So, you know the difference between weighted and unweighted. Until now, what is that we did? We assumed we have only one information, observation. Sometime I may have some prior information about the unknown X. I'm moving now to 3D world. With me? Any issue in the world, you have some idea about it. With me? If you talk about election, everybody has a ton of ideas. If it is politics, everybody knows everything, but no two people agree. With me? So on several issues, each of us, even before we come to play the game is, the class we are playing the game of learning. So before you come to the class, you have some prior belief about what the subject today is going to be. And you come into the class. You remember the Bayesian formula my friend talked about, Dr. Vineet, in the first class? So I'm going to combine my prior, because I don't want to leave my old opinion. Is there anybody who says that I was wrong? One of the hardest things for a human to say, yes, I was wrong. Come on, guys. We'll always say, well, I believe this is so, right? That's right. So we never want to forget about our old opinion because we formed it. It's our opinion. We also learn. So after we learn, something then you get is the mix of my old belief and the new information I have had. That's posterior. Are you in my place? So how do we handle that? Here I have only one information, namely observation. How does this transform itself if I were to deal with a prior information? How do you combine a prior information and a new information coming from observation in the least square framework to be able to get a combined opinion? Are you all with me? Come on, guys. I'm not going to do in the space of probability density function. You remember the base rule he said? The posterior density of x given z is equal to the prior density of x and the observation z given x divided by pz. That's a base rule. I come into the game with some prior knowledge. Then the game reveals some information about the observation. Then, given the observation, I'm going to update. So this is called posterior. This is called prior. He called it likelihood. There are two names for it. One is likelihood, another is called conditional density. A more common terminology is conditional density. This is simply a normalizing factor. This is simply a normalizing factor. So here, I'm not worrying, I'm not updating my belief in the opinion space, but here I'm updating the opinion in the probability distribution space. Are you with me? I want you to understand which space you are working. Now, I'm going to be working in the opinion space itself.
So now onward, will you use the term conditional or likelihood?
Okay. The precise meaning of the likelihood is as follows. P, Z, X. There are two variables, right? If you fix X and consider this as a function of Z, that's called conditional. Now, here X is fixed. If Z is fixed and considered as a function of X, this is called likelihood. That's the standard definition in statistics. So there are two variables. I can fix one and consider the function of the other. If you fix the parameter X fixed and consider this as a distribution over Z, that's called conditional distribution. New information. If you fix Z and consider the function of X, that's called likelihood function. Some people, they use these things interchangeably, nothing wrong. It depends on their taste. But I would differentiate likelihood from conditional distribution, even though they refer to the same quantity, but the dependence is slightly different. Are you all with me? How we are transitioning? Yeah.
For the R value, you have assigned sigma square I.
What that?
For R,
Uh-huh.
you have assigned how?
Sigma square I. So how do I?
How you are saying that value sigma square I.
Sigma square? Oh, okay, good. The voltmeter, let's say 5% accuracy. So 5% accuracy in voltmeter means what? The standard deviation is 5%. Are you with me? That's right. So that's a property of the instrument. That's a good question. Huh?
I is the identity.
I is the identity matrix. Please understand, this is the matrix, right? This is a scalar. So this is the M by M matrix, this is the M matrix. Sigma square I. It's the matrix with the same diagonal element. Got it?
Yes.
Did you see the way she nodded her head? This way. I'm not trying to criticize you. Please take it in a good spirit.
Sir, we are habitual, not in a...
No problem. I'm not trying to change you. Don't change yourself. I'm simply observe. Can we observe? Don't take it offensively, buddy. Are you with me? That's right. Any questions? He's so protective. He's so protective the way he nods his head. That's right. Good. Any questions? Going once, twice, thrice. Let's go over to the 3D war. So, the starting point for 3D war. There's an unknown X. I want to estimate this. I'm going to have two pieces of information. One is called the prior information. The prior information is, I believe X is such that it is distributed according, is a random, so X could be a random variable. It distributed such that E of X, the prior information, I can even say that is normal with XB sigma B, where so the prior information on that is X has a mean and the covariance. And it's normally distributed. Everybody? It doesn't have to be even normally distributed. We can assume X has a mean. So that will be even, simpler assumption. So the prior information essentially says E of X is equal to EXB, covariance of X is equal to sigma B. To say Gaussian is more information, right? To say mean and covariance is less information. So I have less. Then I have conditional density. I have observation. What does the observation say? Z is equal to h of x plus v. And v is normal 0 r. All of it may? Now do you see the two information now? I want to be able to combine the two. So how do we use in practice? What is the reason why we do this? So this is today, present. This is t minus 1. So from yesterday, I made a prediction. The prediction could be xb with a variance sigma b. Then today came, I have my observational network. My observational network gives me z is equal to h of x plus v. And that's what we do in weather prediction, right? I have yesterday's prediction of today. Today comes in. I get today's observation. Then I want to estimate what was the exact weather of today. I want to be able to combine the two. So the weather today is the unknown variable. I can't throw yesterday's prediction because I spent a lot of money in making that prediction. All of it may? So prediction is a sequential process. So knowing today's weather as a predicted value from yesterday and knowing what has happened today, I want to be able to establish what was the real weather today from which I can make the prediction for tomorrow. And then tomorrow's observation comes in. From that, you want to be able to estimate what was the exact weather on that day. I want to keep going. When did they start weather prediction in India? How old is the Indian Meteorological Department? Indian Meteorological Department was established by Europeans, some 1852 or something. Check it. Some site. Indian Postal Service was established by British. Indian Railway Service was established by British. These are the three institutions outside the Indian government. These are the three institutions we have today, the legacy of the British rule. I'm not trying to criticize anybody, but that's the way these things are. Understand? It's an old system. We keep continuing. So we have been doing forecasting. The forecasting system may have changed. The computers may have changed. The people may have changed. The forecasting process, the algorithm may have changed. But forecasting for tomorrow, today, getting today's observation, computing the exact weather today, that process has not. That philosophy has not. That's called sequential prediction. Are you with me? So I would like to be able to combine the two using least squares method. So if I told you this is normal, this will be then prior. This will be then posterior. This will be then the conditional information. I can combine the two. I can use the Bayesian rule to be able to compute the posterior distribution, which is today's distribution. Everybody plays. Posterior distribution is in the probability space. Then how do you estimate the current weather from the posterior distribution? The mean of the posterior distribution is the best estimate of today's weather. All of it may place. So there are different approaches. One is the Bayesian, another least squares. I'm going to, now that he has already done Bayesian, I want to do I want to do the least squares. Are we getting closer and closer to reality? So if you thought yesterday was highly mathematical, hey, we are pretty close. To get here, we needed so much of mathematics. To get here, we needed so much of mathematics. Good. So what am I going to do? I'm now going to concoct a new cost function, which is the sum of two cost functions jb of x plus jo of x, where jb of x comes from this. There is a reason for the subscript b. Sometime in meteorological circumstances they call it background. B for background. Are you with me? The rose smells the same by whatever name you call. Shakespeare, Romeo and Juliet. Are you with me? The properties of the flower called rose doesn't change because you call it rose. All of you? The rose is a rose by whatever name you call. Shakespeare, Romeo and Juliet. You needed a name, I needed a name. My properties would not have changed if instead of Varahan, I was something else. So names are labels. Labels are not you. You are identified by a label. Are you with me? That's right. That's right. So I want you to be able to understand the properties, the labels, and the functionalities and so on. So what is JB? JB is equal to x minus xb times sigma b inverse x minus xb transpose. What is that? Oh, well, then what is xo of x is equal to z minus h of x transpose or inverse z minus h of x. Now, do you see he's our old friend? How many of you are with me? Without this we saw yesterday, with this we saw today. If I had observation, I would have only considered J naught. I have another information. I'm going to combine the two. So this is the combined objective function. So what is that I want? I want my x to be such that it is not too far away from xb. I want my x to be such that h of x is not too far from z. Compromise. Are you with me? Come on, guys. That's right. Life is full of compromises. Compromise is good. Do you see that, please? So what is x? X is unknown. What is the x? The best estimate of today's weather. The best estimate of today's weather is not going to be too far from yesterday's prediction. It's not going to be too far from what the observation today comes in. I would like to be able to compute x being the best. Is the formulation clear? How many have heard me? That's right. My formulation is done. So what is next? Compute the gradient, equate the gradient to 0, compute the Hessian, make sure the Hessian is symmetric past definite, you get the estimate, get on with life. All of you with me? So understanding the fundamental principles of data assimilation is very easy. And that's what I'm trying to make it. That's why I started from the fundamentals. Are you with me? Now what is this? This is the quadratic, this quadratic function is the same type as this. So I multiply this. So if I multiply this, what do I get? X transpose sigma b inverse x minus 2 times x transpose sigma b inverse xb plus xb transpose sigma b inverse xb. And what is this? We already know this. Now, z transpose R inverse z minus 2 times Z transpose R inverse H of X plus X transpose H transpose R inverse Hx. There are 6 terms. This term is independent of X. This term is linear in X. This term is linear in X. This is quadratic in X. This is quadratic in X. This is independent of X. So if you compute the derivative with respect to X, the derivative of this will be 0. The derivative of this will be 0. The derivative of this will be a derivative of the linear function, quadratic function, quadratic function. We all know that, how to do that, right? How many of us may? How many of you know of 3D war? How many of you have heard of 3D war? How many of you know of 3D war? Having heard, you heard in a party, right? You heard in a lecture. I heard it exists, but I don't know what it is. So that is the known unknown. Aruzmina? I know there is something called 3D war. I keep hearing wherever I go, but I don't know what it is. It's a known unknown. By doing it, I'm going to make it known. That's learning. Yeah. I have a hearing problem. You may need to use your, please. Check the volume.
So as I have seen earlier in 3D formula, means like x minus xb, which you have taken.
No, you started too fast
in
for
both
me.
jb and j naught means.
So we have these 2 terms, right?
Yes. So normally we get in both the formula we get the true state means like x minus xb, as much as I remember, and x minus h of x like that. I think true state. Then here z is different and x is different. So I'm not able to relate.
Did you hear what she said? I have seen something earlier, right? Okay, what is the difference between what you know and what it is? Tell me the difference.
So here x, as you have told, it's a true state of the atmosphere.
This is the background state.
Background state, and x
This
is the true state.
one by one. This is the new information.
Huh.
So this is the unknown. This is the unknown. I want to find the x such that h of x is close to z. I want to find x such that x is close to xb. We already know how to make x such that h of x is close to z previously. Are you with me?
Yes.
That's right. Now, my job is a little bit more difficult. Earlier, I had only one goal, to find x such that h of x is close to z. Now, there are 2 forces pulling me. I want x to be close to xb. I want x to be such that h of x is close to z. These are the 2 forces I need to find where the equilibrium is. And that's the problem. Got it? That's right.
So, actually, suppose we have a truth value. Truth is not known. Everybody knows that.
But then, good.
Truth is not known.
Truth is not known, that's right.
But suppose if I am talking for a single point, so we will assume that there is a reference. Let's say I am talking for today's temperature.
You are unnecessarily trying to complicate it. Here also I am using the same thing. There is a point x. X is a point in the n-dimensional space. Are you with me?
Yes.
So I'm not trying to talk to you anything differently. There is a state x in the n-dimensional space. I don't know where it is. Good. Let me erase this and then we will start the discussion. Good discussion. Good discussion. So there is an n-dimensional space. There is an xb. There is a okay, maybe I should do it a little bit better than that. So this is the model space. This is the observation space. There is a z here. There is a xb here. I want that x, that h. Are you with me? So this H is related to, let me simply say xz. So xz is the guy, so that means z is equal to h of xz. That comes up from here. So this is what I would have gotten had I just used observation alone. Are you with me? But you gave me something here. So I have a line joining the two. Are you with me? So here's a point. That's a point. Yesterday's prediction tells you today's weather is closer to here. The observation tells you that it is closer to here. So there are 2 points. I can join the 2 points by a line. So what does the theory say? The truth must lie somewhere between the line joining xb and xz. Are you all with me? That's right. That's it. Is it a real truth? It's an approximation to the truth. His comment is very well taken. I ultimately want to estimate the truth. Can you know the truth? No. You can only approximate. So the approximate truth lies on the line segment joining between xb and this. So if you don't have the observation, I will go with xb. If you don't have the xb, I will go with xz. If you give me something, I want to make a compromise between the two. And how am I going to make the compromise between the two? Using the 3D one. You all have an aha?
Wow.
That's right. Wow, that's right.
Sir,
Yeah.
in
You didn't say wow. See, have you seen, some people will ask a question. You answer. Then they won't say, yeah, thank you for that answer, but I have a follow-up. But they won't say that. But, are you with me now? That's what you said. Is the whole answer clear to you?
yes.
That's right. Say, acknowledge, guys. That's what I'm saying. Enjoy the answer as and when it comes. So his question was, where the truth lies. Aha. Say aha. Good. I hope I'm not forcing you. He said, wow. I hope you are a follow-up now. Is that what it is? Please continue. In other words, I want to give a context to people. Are you with me? Each question is important. I want to enjoy each question in its purest possible way. I want to, the new question, not mar the result of the old question. Are you all with me? You could not jumble questions. That's all what I'm trying to tell you. Good. Go ahead now.
Sir, in every iteration, yeah, every estimation, we are transporting and interpolating a model value to observation value. Why we are not interpolating this observation value to model value?
That's what we did. This is x star. Instead of calling xt, this is the least squares. So observation is one space. Model space is here. My prior information lies in the model space. The observation lies in the observation space. I want to combine the two. So what is that I need to do? I need to bring the information contained in the observation from the observation space to the model space. He's not nodding his head. He's a tough guy. Are you with me? That's exactly what I'm doing. So what is x star? X star is the solution to the least square problem if I had known only z alone. That's what we did so far. Then you gave me a prior. So in the model space, earlier I did not have anybody. He was the king. Now there is somebody else in competition. If there are two competing information, I want to take a compromise between the two. The solution to this problem is going to be a compromise solution that will lie on the line segment between xb and x star. Is that an aha? That's right. So even that I had to pull it out of his mouth. Come on, guys. With me?
Yes.
That's right. So you need to understand where the information lie. So in 3D war, one information lies in the observation space, another information lies in the model space. I want to be able to do computations in the model space. Why do I want to do computation in the model space? The observation space is larger than n. Computation in the larger dimensional space is more expensive than a smaller dimensional space. So there are observation space calculation, there are model space calculation. Since m is greater than n, I prefer to do computations in the model space. Are you all with me? Come on, guys. That's right. That's right. You see, that's a beautiful pictorial explanation of what's going to happen. So what is it I now need to do? I need to compute gradient of j. Gradient of this j. So what is the gradient of this j? The gradient of this is 2 sigma b inverse x minus. Now let me rewrite this part. This is equal to 2 times xb transpose sigma b inverse. Maybe I'll write this a little slowly. So let's consider this term. Do you know this is a scalar? That's right. So x transpose sigma b inverse xb is equal to x transpose sigma b inverse xb transpose, because the scalar is equal to itself. The product of this is xb transpose sigma b inverse transpose x. But sigma b is symmetric. Sigma b is actually SPD. Sigma inverse is also SPD. That's a theorem. Inverse of a symmetric positive definite matrix is also symmetric positive definite. If sigma inverse is symmetric and positive definite, it transposes itself because it's a symmetric matrix. Therefore, are you with me? Therefore, this term is equal to this term. So I should be able to rewrite this without loss of generality, xb transpose sigma b inverse x. All of it may? Now, this is the linear function. I'm going to consider this as A transpose. This will be A transpose x. The derivative will be A. A will be sigma inverse xb. Therefore, this is sigma b, there's a 2 sigma b inverse xb. That's the derivative of that. The derivative of that is 0. So that's the first line. The derivative of this is 0 minus. What is the derivative of this? This is A transpose x. So this is that. So what is A will be H transpose R inverse Z with a 2 here. And what is the gradient of that? That's equal to 2 times H transpose R inverse H of x, and that must be 0. This is not data assimilation, this is multivariate calculus. Are you all with me? That's right. Estimation theory is applied mathematics. Data assimilation is estimation theory in large. So 2, 2, 2, 2 gets cancelled. I'm going to have to simplify this. I will write that equation in here. Now you know, I have slides for all these things. Now you know why I don't use the slides. In the slide, I will say it can be shown, it can be shown, it can be shown, it can be shown. All of you would have gone to bed by then. I don't know what the hell is happening. Please give me a copy of the slide. I may try to read it. You put it in a computer, never look at it. Are you with me? Human beings, we all know how to collect junk. Our computer contains a lot of junks. I want to tell you a story. I went to school in the late 60s and early 70s. There was no Xerox machine at that time. You cannot Xerox any paper. There are simply no Xerox machine. So PhD students, especially like me, theoretical work, we used to have a table in the library with my name on it. Nobody will touch it. I had a table reserved for me in the library for 3 years. The only way for me to work is to be able to go to the library, get the journal, read it, and write a summary of what I have read, and my knowledge of the paper is my summary. I cannot bring anything home to read. Are you with me? So that forced me to read journals right there, then and there. So I used to have a file, handwritten file, which then I brought it to my room and what in the hostels. Today, what do we do? Oh, get me a copy. I do too. Not only you, yeah, I do too. I have so many papers at home. I thought I will read it, but I never got to it. We collect junk, and computers are full of junks. Send me a scanned copy. Send me this. How often you look back to your directory to see, what is that I got? When did I read this last? Are you with me? The reason I'm trying to tell you is one thing to have it is another thing to read it. Are you with me? All the notes I have forwarded to Dr. Kutty, and he is going to make arrangements to sending to all of you. I'm giving you a 100-page appendix from my book free to everybody. All of you? That's right. So you will get it sooner or later, all the slides. But I'm trying to talk about the details of the slides. Good. So let's try to write this equation. So I'm going to keep the terms. This is the x. This is the x. This does not have x. This does not have x. Keep the x terms on one side. Keep the term that does not have x in the other term. Collect the terms. So that, when simplified, becomes sigma b inverse plus h transpose r inverse h times x is equal to sigma b inverse xb plus h transpose r inverse z. Wow. When there is no background, this was not there, this was not there. I only had that equation. That's the equation I got earlier. When you don't have observation, I don't have this, I don't have this, I only have this. Everybody? But when I have both, I got this. So what is the actual value of the estimate? So x star is equal to sigma b inverse plus h transpose r inverse h inverse times sigma b inverse xb plus h transpose r inverse z. Hey. Now look at this now. This times xb, and this times z. All of it, my place? That's right. And that's exactly what I talked about. Here is xb. Here is the information contained from. Here is the information contained from x star from the least squares. And I'm going to draw a line. So what is the best way to understand this? The best way to understand this is as follows. This is equal to sigma b inverse plus h transpose r inverse h inverse sigma inverse xb plus sigma b inverse plus h transpose r inverse h inverse h transpose r inverse z. So this is xb. This is the one that comes from the z. Are you with me? Now look at this now. H transpose, so here is the model space, here's the observation space. H takes you from here, H transpose takes you from here. Are you all in my place? So R inverse is essentially a normalization of that. So H transpose transfers the thing from here to here. So I get these 2 points. So this is the weighting for Z, this is the weighting for XB. So the linear combination of these two. And that's exactly what I have been talking about. XB and Z. XB and H transpose R inverse Z. That's the model space. All of you? Come on, guys. Everybody should have an aha. Why? If you know this is an affirmation, you should have an aha. If you didn't know, you must have an aha. If you must have a louder aha. I did not know, now I know it. Wow, I learned it. So let me hear. Come on, guys. Hope you had a good paratha this morning. Say aha. That's right. Every way you are a winner. If you know, it's a reaffirmation. If you didn't know, you are learning. So there is no loser. Are you all with me? That's right. I'm later going to show this is exactly what Kalman filter does. Kalman filter has 2 parts. One is the prediction part and is the data assimilation part. The data assimilation part in Kalman filter is equivalent to 3D VAR. If you know what Kalman filter is all about. If you didn't know, you are learning something. So what is Kalman filter doing? In one step I create XB. Prediction from yesterday. And then I get the new information. I combine the two. So there's a predictive step, there is a data assimilation step. The predictive step is simply running the model. The data assimilation step is combining 2 pieces of information. Combining 2 pieces of information can be done in one of many ways. 3D VAR was done in the 80s within the meteorological community, but Kalman filter came in 1960 within electrical engineering. I want to tell you, I was a student at Indian Institute of Science. In 1971, Kalman came to the institute and gave a lecture. I had the good fortune of listening to Kalman filter from Kalman himself. Oh, he's a fantastic lecturer. You have to see him the way he works on the blackboard. It's an inspiration to watch people like him. So the Kalman filter came within the electrical engineering committee in 1960. Meteorologists took notice of it only in 1982-83. Meteorologists are latecomers. I'm sorry, I'm not trying to put you down. The principles of 4D VAR, we talk about in meteorology, that also came in 1985. But it is known in the control literature as early as 1950s and 60s. I happen to have a training in control theory, master's in control theory from Indian Institute of Science. So I could very easily talk to meteorologists, whether it is a 4D VAR, whether it is a Kalman filter, because I've been introduced to the tools from control theory, estimation of parameters in control systems, Kalman filters using estimation of states. So even though I come from an electrical engineering community, in 1990 I went to my meteorology department to hear a lecture. Then at the end of the lecture I told him, hey, your language is different, my language is different, but we are talking about the same mathematical entity, let's get together. So I've been working within the context of meteorological atmospheric science related programs since 1990. Are you with me? I'm not a meteorologist. So what does it tell you? To be good in data assimilation, you don't have to be a meteorologist. But to be able to know the model, the data, and the ultimate use of the data assimilation is meteorological forecasts. So if you're a meteorologist and if you can specialize in data assimilation, more power to you. With me? Yeah, with that we will stop, we'll take a break.